So we are into the third day of this FDP on design and analysis of algorithms. This morning we have with us Professor Madhavan Mukund from Chennai Mathematical Institute to handle a session on greedy algorithmic techniques. Professor and Dean of Studies at Chennai Mathematical Institute. He received his BTech in Computer Science and Engineering from IIT Bombay. He did his PhD in Aarhus University, Denmark. His research interests are models for concurrent and distributed systems, formal verification, and distributed algorithms. He is the president for Indian Association for Research in Computing Science, and he is the vice president in India, and he is the national coordinator for Indian Computing Olympiad. He is in the editorial board of Leibniz International Proceedings in Informatics, an open access series for conference proceedings. And he has been program committee member in quite a lot of prestigious conferences. And he has been very much instrumental in making this program happen. He is part of the ACM India Education Committee, and we have been talking about such high quality FDPs for the past 6 months, and this is the first one which is happening with the sponsorship from ACM India, and he is also involved in giving a lot of MOOC, massive open online courses. Both the first day I was mentioning about an effort from Microsoft, and he has given a lot of sessions as part of that. And he is also involved in NPTEL MOOC courses, variety of courses, design and analysis of algorithms, and also Haskell and concurrent programming and other subjects. And he has a very unique style of teaching, and with the way in which he writes and explains it, I am a great admirer of his teaching style. Thank you very much, Madhavan, for coming down here for this. Thank you. Yeah.
I will not be using directly my slides, although I do have slides. I will try to write on this. Let's see if it works. Okay, so the topic for today is greedy algorithms. I think you have had a little bit of an introduction to this yesterday in the dynamic programming class, but I will start, of course, from scratch since this is your first formal lecture in this course, at least on greedy algorithms. So let us start maybe with an example. Have certain values of, okay, so for example, in an Indian context, you might have 500, 100, 50, 20, 10, 5, 2, 1. Okay? So typically, this is the kind of unit that you can return change in. And now supposing you want to return 276 rupees is change. Okay, and now, of course, there must be a goal. The goal is that you want to use minimum number of notes and coins. Okay, so you can assume that you don't have a shortage of currency. So you have as many hundreds, 500, 50s, 20s, 10s as you need. So what would be a good strategy? Now I want to return 276 rupees. I have unlimited supply of money with me. And I want to return the minimum number of notes and coins, number of pieces of money back to this customer. Right? So what would I do? much is this? 2 plus 1 plus 1 plus 1 is 6. So how did you get this? Right? So, I mean, what you try to do is, it seems reasonable that you reduce the amount of money you have to give back as much as possible with each piece of money that you take, right? So you wouldn't start with a 1 rupee note, a 1 rupee coin, because that will still leave you 275 rupees to give back. So you can't use 500 because it's less than 500, so you try to use 100. So that reduces it to 176. You can still use 100, so reduce it to 76. Now you can't use 100 anymore, but you can use 50. Okay? So this is an example of a greedy strategy, right? So this is a so this is how we did it. Right? So we start with the 276, we pulled out a 100 rupee note, brought it down to 176, and so on. So the goal was to kind of, so you want to maximize this drop, right? So we want to use up as much of the balance as possible with the given thing, right? So why is it greedy? Because having decided that this is our strategy, we do not consider, we did it once, it worked for the first 100. Now I'm left with 176. We don't think about, oh, maybe if at this point, should I use a 20? You say, okay, I've stuck to this strategy, so I will, so it's kind of fixing one particular sequence, right? And you're never going to go back and say, oh, at some point, I think that maybe it was not a good idea to start with 100. Maybe I go back and start with 50. Okay? So next question you have to ask yourself is, so now, of course, the question itself needs to be clarified. What does it mean always? Okay? Always has a narrower interpretation and a so one possibility by always is we are working with the same set of values, 500, 100 and all that, but we have different amounts to return. So instead of 276, I might want to return 343 or something. Okay. So this could be one interpretation of always. That is, I'm still working with our currency that we normally deal with. Does it work for every scenario that shopkeeper is going to encounter? Assuming, of course, that he always has unlimited supply of all these things. Right? So if he doesn't have hundreds, then this strategy won't work. So, and that is usually the problem. But that's not going to be the problem here. Right? So here we assume that there's no shortage of change as such. It's just that he wants to. Okay, the other point is that you could have different types of currencies. So maybe I don't have 500, 100, 50, 20, whatever. Maybe I only have something else, say maybe 50, 20, and 1. So one of the things that we will see today is that when you come up with a greedy strategy like this, first of all, you have to justify that this is correct for 276. Right? So you have to show that I did it with 6 pieces. I cannot do it with less than 6 pieces. There may be a different way to do it with 6 pieces. That is okay. Supposing I had, instead of a 1 rupee and 2 rupees, supposing I had a 3 rupee coin. Then that last 6, instead of 5 and 1, I could have done it as 3 and 3. I would have still got the same number of coins. So the number of coins or nodes, there may be different ways of getting the same result, but you have to show that at least this is as good as anything else you can get. That is the first step for this example. Then you have to ask whether it works for all examples. Does it work regardless of the amount? It's not 276, but some other amount, will it still work if I just follow? So the strategy is now fixed, right? I take the largest note I can pull it out, and so on. Does this strategy always work for the given set of values which I am allowed to return in terms of the coins? Then the next thing is that if I change my situation, if I go to a different country where the coins and notes are of different denominations, will it still work? Right? So what do you think? What is your instinct about this? Do you think this strategy will work, for example, in the first setting? That is, if I change 276 to some other number, but I don't change the remaining part of the problem. I still have 500, 100, whatever. Okay? So do you think it will still work? How many people think it will work? How many people? There are many people that think it will not work, or they think that it may not work. So if it will not work or may not work, then you have to come up with a, if you believe it does not work, then there should be a situation where it does not work. So you have to come up with a counter example. If you claim it works, then you have to prove to me that it works. Okay? I don't know how to prove this, but for this particular case, but so this is probably correct. Okay? But this I claim is wrong. It will not always work. Suppose, for instance, I have a smaller set of denominations. So here is a set. So do you think that this strategy will work with this set? That is, I always choose the largest note or coin that I can use, then reduce it and so on. Okay, so you need either a proof which is harder, or if it is no, if it's enough to produce even one situation where it doesn't work. Okay, so I'm telling you in advance that it doesn't work. So tell me a situation where it doesn't work. What does the greedy thing for 60 say? Take the largest one, and then I'm stuck, right? Then I have to do 1, 1, 1, 1, 1. Which gives me 11 pieces. Because once I've reduced it to 10, then I can't use a 20 anymore. So then the only way I can make up 10 is by using 10 ones. What should I do instead? So I can instead do So therefore, it is clear that it doesn't always work. I mean, how you find an example like this is a different question. Okay? But the point is that greedy strategies in general are tempting but rarely work. The fact that they rarely work is unfortunate because they are usually very simple. Okay? But that simplicity is the problem. The problem is that you're trying to make a choice now based on the information that you have now, which is optimum at this point. So it's a bit like, you say, supposing you are here in SSN and you want to go to Avadi. And you've decided that you'll go by bus. So now you go out, and one strategy might be that the first bus going north on OMR I will take. Or the first bus going north on OMR might be stopping at Kedambakam. Okay? Or it might be going all the way to T Nagar. Or it might be going somewhere in between to Tirvanbur. Or it might be going somewhere further away, but it might be going off OMR in the wrong direction. It might be going 570S, might be going off towards this side, Vadapaindi. So then depending on which bus you take first, then it forces you to get down and take another bus. And then from that point, you have to solve the same problem. So you again may decide you take the first bus which is going in the direction that you, general direction. From there, you decide that from where I am now, the best way to get to Avadi is to take this road. So whichever bus is going in that direction that comes first, I will take it. And I will get off at the first point where it deviates from my path. Right? So this is a greedy strategy, where the greediness is that you don't want to stand at a bus stop. Another strategy might be, I will take the first bus. Okay, so you can't actually do that. Okay, so better strategy might be, I want to take a bus which will take me as far as possible. But I'm sitting at this bus stop, I don't know when the next bus is coming. It might be 1 hour away that I have a direct bus to Avadi. Whereas if I take that first bus which came and took me up to Adyar, for example, it's quite possible that I will reach much before that bus. Right? So this is the advantage of this greedy strategy. It allows you to make quick decisions and keep moving. But you can never rule out the fact that 5 minutes later there was a better bus, which would have taken you all the way. Okay? I can no longer use 50. But from 59, I can do all. I can use 50 and get it to 9. I can do 20 and get it to 39. I can do 1 and get it to 58. Right? So what we are saying is that the actual solution corresponds to one of these. So each of these things I can now complete. There will be some choices from here, 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 and so on. Okay, and what we want as our solution, right, is the best among all these different sequences that we could possibly do. Right? And what is greedy telling us? The greedy is telling us that at every point, the next choice that I make, I determine by some predetermined rule. So in this particular case, greedy tells us, so greedy will tell us in this case that, okay, choose the biggest one here and then choose this and then go down. Right? Don't look at that side at all. We never even examine what might happen. Whereas if you remember what dynamic programming does, it would say, okay, my first choice is this, this, or this. Okay? So then I've used one coin, and then you set up a recurrence. Right? My choice is to use one coin and solve 10, solve the problem with input 10, or use one coin and solve the input with problem 40, or use one coin and solve the problem with input 59, and choose the best among these. Right? So dynamic programming is essentially exploring all these choices, but what it does, what dynamic programming as a technique does, is it makes sure that when you're exploring all these choices, you can notice that this, for instance, 39 has come here, and this 39 has come there. Right? So if you do it by brute force, you will solve the problem for 39 as a part of solving it for 40. You solve it as 39, again as a part of solving it 59. Dynamic programming will say, don't solve it twice. It will say, keep a track of what all problems you have already solved, and if you have already solved it before, look it up in a table. Okay? But other than that, dynamic programming ensures that you do not ignore any option. So dynamic programming, in a sense, is always correct. It is trying to optimize some value, but it is not ignoring any possibility. Greedy, on the other hand, is taking some step based on some current criteria which seems to be attractive, and it is never going to go back and change that option. You are never going to go back after choosing 50 and say, oh, maybe 50 was not the right thing to do. Whereas dynamic programming says, okay, if you choose 50, solve 10. If you choose 20, solve 40. If you choose 1, solve 59. Tell me which among them is the best, and then decide whether to choose 50, 20, or 10 as the first step. Right? So that's the big difference. So this choice is never the choice you make is never reconsidered. Okay, that's the crucial thing. And because you never reconsider it, you have to justify that that choice is sound. And as we saw in this example, it doesn't work. And I claim that for that 150, 20 thing example, it works. You can see the big difference. The big difference is that you cannot make up 50. I mean, there are multiples of 20 which don't add up to 50. Whereas in the other thing, if you can see 1, 2, 5, 10, 20, 50, 100, if you can do things with 50s, then you can group them and do it with 100s. If you can do things with 20s, again you can group it and do it with 100s. Okay? So you can kind of argue that that is the real thing, that at any point if the smaller things can be kind of done by the bigger thing in multiples, then you're okay. So there is a kind of way to solve this problem in the sense that if I give you the values, like instead of 50, 21, supposing I gave you some, I have a 73 rupee note and a 36 rupee note and a 14 rupee note, then can you do it, right? Of course, if you don't have a 1, then you're in trouble because you won't be able to give change for other things. Let's assume you always have a 1. So there are actually algorithms which will determine whether or not for this particular set of values, greedy works or does not work. So for some it works, for some it does not work. Right? So here, for instance, for this choice, you would need to use dynamic programming to get the answer. Okay? So this is an example to just illustrate that a problem, depending on how it is phrased, a greedy strategy may work, may not work. And if it does work, you're obliged to show that it works. It is not something that you can assume it looks like it works on this example, so it looks like a good strategy. It might work on one example, may not work on the next. So even this 50-21, okay, supposing I give you 50, for example, as the input, not 60, then it would work. Right? You just give 150 rupee note back. If I give you 40 also, it will work. You give 220s back. If I give you 70 also, it will work. You give 150 and then 120. So 60 is a kind of bad case. So there are some good examples and some bad examples even within this. It's not that greedy will always fail. Therefore, you need to either find the counterexample or you need to prove that it works well. Just isolated examples, if it works, it doesn't help you. Okay? So with this background, I will now go to some I want to do some textbook examples, and through these textbook examples, we will explain the kind of proof that you need to give. Okay, there are basically only 1 or 2 things that you can do, but each proof is always a new proof. So I just want to check. So the break is at 10:30. For coffee. So there will be 2 examples, and they both come from broadly from this scheduling thing. So okay, so let us just get back before I do this. So let us just kind of spell out what greedy means. Okay. The first thing is that you find some Right? So the situation is typically that you have to optimize something. You want to minimize something, maximize something. Okay? So in that bus example, you want to reach your destination in the minimum amount of time. Okay? This involves making some choices. Should I include this? Should I exclude that? Should I take this bus? Should I not take this bus? Should I use this node? Should I use that node? Okay. And now the greedy thing says, that we have some kind of a way of measuring what is going to happen if we make a choice. The change example, the measure is that basically we want to reduce the amount of change which is still remaining to be given, okay, by in the bus example, we are going to minimize the amount of time we spend waiting at a bus stop. And we are hoping that this change that we observe locally, which we can decide immediately, will overall give us a best solution. Okay? So this gives us a so now given the way the input is given to us, okay, so we are presented with this 276 or we are presented with some other thing, then making these choices forces us to do things in a particular sequence. We don't have much choice after that as to what order to do it. So in the change making thing, we always use the biggest node that we have available. In that bus example, we always take the next bus that comes in the direction that I'm going. So you might choose to ignore a bus. Here you may not be able to use a denomination. You can't use a 50 if your value is less than 50 and so on. But other than that, your next move is fixed. Okay? And the hope is that this converges. So now the problem is the following. Right? So in general, so you might have something like you have each item is or is not part of the final solution. For example, supposing I have 276 rupees to return, then it should be obvious that I cannot possibly need more than 276 different pieces of currency, okay, because I have 1 rupee. Supposing I have 276 1 rupee notes, 276 5 rupee notes, 276 10 rupee notes, and so on. Okay? So I have some 6 denominations. I have 6 times 276 pieces of currency in front of me. What I have to do is decide which of these guys I'm going to use. Okay? So this is a kind of very brutal example, but the other example in the bus thing is that I have a number of buses which go past me. Okay? And maybe there is a window, maybe looking, although it doesn't happen in real life, but maybe over the next half an hour I can see all the buses coming in front of me. I'm going to choose the next bus using some criterion. So all the possible buses that come in front of me are available to me. Some number of those buses I'm actually going to choose. Of course, there will be some buses at the first bus stop, some at the second bus stop, and so on. Or in general, for example, you want to put things into a, say you're trying to put things into a room, okay, a storeroom. So you have a lot of furniture, you have to vacate your house for whatever reason, or your hostel room or something, right? Not everything is not going to fit. So you have in front of you 2 cupboards, 1 bed, 1 chair, some suitcase with your clothes and all that. You have to decide what goes in. So some subset of this is going to fit. Maybe you want to put as many items as you can into that thing in terms of pieces. Right? In all of these things, you have a number of input items. You want to choose some. Okay? And you want to choose some such that it satisfies some optimum criterion. And maximum number of items go into it, or they have some value. So the total value of the things you put in that storeroom is highest. So maybe the suitcase is not valuable. You don't want to put it. Maybe your cupboard has got a lot of things stored inside it. You want to put that in first. Right? So in each case, you have some n input items, and you have to either for each item either pick or not pick. So how many such choices are there? Right? So you have item 1, say yes, no. Item 2, yes, no. So how many choices are there? 2n. So think of it as the first thing is 0 or 1. Second thing is 0 or 1. Right? So I have n bits. So I have 2 power n. So I can read it off as a number. Right? So I have n bits, 1 bit for each item, and that bit is either on or off. There could be some stupid solution which has nothing there. It could be I could be lucky and everything might be, I could maybe put everything in the storeroom. Okay? So I have 2 to the n choices. Solution. Right? And of course, depending on how I order them, it's different. But the point is that the greedy only chooses right? You never go back and reconsider, oh, should I have put that cupboard in that room? You look at the cupboard, you may not look at the cupboard at all. You might decide that right now there's no space for the cupboard, so you just throw it out. But if there is space for the cupboard, you will look at it and decide whether it goes or it doesn't go. You'll never look at it again. So you make at most n choices. Okay? And in the process of making at most n choices, you have to somehow navigate the space of all the solutions efficiently. So there's a good reason to believe that this will not work. Okay, you're not doing enough hard work in order to find the optimum. You're trying to find an easy way through this thing. Okay, and that is why this thing is called greedy. You know, you're trying to accumulate as much value as you can from the next move without thinking about what happens later. Now let's get back to this textbook thing. So there is the following, so let us call it so you say you have an auditorium. So there is one auditorium in your institution. Okay, and you take bookings. So there are events. So supposing somebody wants to hold a quiz competition which takes 2 days, and they want to hold it on 8th and 9th. Somebody else wants to hold some sports meet, and it starts on 9th but goes on till 15th. Okay, and they want to use the auditorium for some activity. That somebody else wants to hold a dramatics competition, and that will require from 1st to 6th. Okay, so there are different events, and each of them requires the auditorium for some length of time. Okay, so there is an interval. So here is, let's see the picture. So supposing I take, let us take this month. This year's February. Then maybe I might have some drama contest which requires me to go, say, maybe from 3rd to 7th or something like that. So then I might have some other quiz which goes like this. Then I might have some other things goes like this, and so on. Right? So like this I might have many different possible people who have come to me saying that they would like to use it for different things at different times. So now the goal that we have is to keep. So we are not trying to make money out of this whole thing. We want to keep as many people happy as we can. The goal is to so we are not trying to maximize the number of days it is used or something like that. We're just trying to keep as many people who ask for it happy as can. So if we can host 7 events each of one day, okay, it is better for us than hosting one event of 28 days. So we want to maximize the number of events that we host. And clearly overlapping events. Right? So you can't tell somebody that you hold the first 3 days of your competition here and then please vacate because somebody else is doing it. Right? So that's not allowed. Right? So, for example, if you hold either this or this, they can't hold, you rule out this. But then you can hold this and this. But if you hold this, you can rule out these two, and so on. Right? So there are many different choices that you could make. So here, let us just try to list out some. So here is one strategy. So maybe I choose this. Then it's not clear, but maybe depending on how I have drawn this, maybe this way I can do this. And maybe I can do this. I can't do the blue one, and then I can do this. Okay. So this may be one strategy where I can schedule 5 events. There may be another strategy which does something else. This is another way to do 5 events. But if I make a wrong choice, for instance, after this, if I schedule this black thing, it will rule out both of these and I'll only get 4. So assume we have the bookings given to us for a period like this. For each of the bookings, we are told when they want it. Starting date, ending date. And they need it for the entire period from the morning of the starting date till the night of the ending date. So the whole day is gone and we cannot put 2 things together. And I want to keep the customers happy by giving as many events as possible to say, maybe in my annual report, I want maximum number of entries for events held during February. Okay? So it doesn't matter whether I get revenue from this or not. What rent they are paying is not important. So now what is the strategy? So first of all, because it is in today's lecture, there should be a greedy strategy. So the question is, what is the measure that we want to use? That is true, obviously. So if I choose, but am I going to choose one at a time? So then should I start with the very first one and then take it? Sort by finishing date. Okay. Is there any other strategy that we can use? So if you remember the change making thing, right? So what we were trying to do with the change making thing? Right? So we were trying to reduce the problem to zero as fast as possible. Here, what is the thing? We need to keep the auditorium available as much as possible. Right? So another natural strategy might be, if you take a job which, or a thing which is only one day, then it leaves you 28 days to play with the rest. So that might be a valid strategy. So you take the shortest thing. Okay? Or you can start with the one that begins first, or you can start with the one that ends first. Or you can also look at, okay, so there are many different. This the justification for this is that it leaves maximum amount of time free for other events. Okay, the other thing which I explained is possibly a good thing to do. Right? So you pick an event. So what is really important is how many other events are ruled out because this event and that event share a day. It might be a one-day event, but if a lot of other events pass through this one day, then all of them are now kept out. Even though a lot of days are free, you have picked a crucial day. Okay, so maybe there's a very convenient Saturday in the middle of the month, and somebody comes and says, I want to hold an event on that Saturday. But every other event is a longer event, passes through that Saturday. Then in one shot, you have killed all of them. So you might want to choose the event with minimum number of conflicts. So I'm just saying that from this greedy, the way we look at the objective is to squeeze in as many things as we can into this space. Then these are two reasonable questions that you might want to, reasonable measures that you might want to optimize on. One is how much time the first event that you choose. Remember, we're making a choice one at a time, right? So we are going to, essentially what this means is we are going to sort the events in terms of their duration, look at the shortest event. If it is still allowed, given what choices we make, initially, of course, it will be allowed. Then look at the second shortest event. If it does not contradict the first choice we made, take it, otherwise drop it, go to the third shortest event. Other way is to say, choose the event which has minimum number of conflicts. Put it in, throw away everything which is no longer possible. Among those, choose again the minimum number of conflicts. Okay, so this is how it would work. And then we can go to other things, which is to go basically left to right or right to left. So what you do is you just start with the very first event, okay, the one that starts earliest. Choose it. It will conflict with some things which start midway through that. Throw them away. Now choose the one which is earliest, which is after this end. Choose that and so on. So that would be choosing left to right by starting time. Conversely, you might choose left to right not by starting time, but choose the one which ends first. That is, it leaves maximum amount of time free later on. rest of the month. So anything which ends, overlaps with that, throw it away. And so on. So there are several different greedy strategies. Right? So then one has to then ask, first of all, is any of them correct? Or are more than one correct? Or none of them correct? And if one is correct, how do you prove it's correct? And so on. So let's go through them in that order just for now. So is this correct? So remember what I said, right? You could have a short event which overlaps with other events which are longer because it has some prime time. So if I choose to give it to that short event, I might rule out other events which maybe they don't have any problem with each other. Okay? So a typical example would be that I have maybe two long things. I have one short thing. Now if I choose the blue thing because it is the shortest event, it forces me to cancel both the black things. So once you find an example which doesn't work, you can abandon the strategy. The strategy, there's no hope. Okay? So this doesn't work. So minimum conflicts basically says that you want to choose the one which, if you take it, will minimize the number of other things which are ruled out. Right? So this also doesn't work, let me tell you. So what you have to do, suggest to me a situation where it doesn't work. What you can do is, for instance, you can think of this, right? So supposing I take the same example. Now, the blue thing conflicts with both the blacks, but each of the black thing conflicts only with the blue. So if I take minimum conflict, this would work. I would choose the two blacks instead of the blue. But I can expand this example to make sure that I still choose the blue by making blacks have more conflict with something else. So supposing, for instance, I produce some So now what happens is that in this whole set, all the red guys have a lot of conflict because there are 4 or 5 or several things stacked up all in parallel with each other. So they're all in conflict with each other. Okay? Now if I choose the blue thing, then I can do one red thing from the left, any one of them, and one red thing from the right, any one of them, and the blue thing. So I can do 3 things. And the blue thing has minimum conflict. Okay? But if I want to get an optimum, I should actually choose the 2 blacks. The 2 blacks and the 2 reds on the extreme. The top row is really the good solution. Okay? So a variation on that tells me that minimum conflicts also doesn't work. want to do left to right by starting time? This is simpler than it looks, because I could just have one stupid event. It starts on day 1 and goes till day 29. Okay? I could have one that goes to 29. So I'm forced to take it because it starts on the very first day. And in parallel, I could have had several short things. But they start strictly after the first day. Right? So if I pick the first thing that starts on day 1, it might be something which just occupies a long interval and prevents me from doing it. Okay. So I'm not saying that it's obvious that these strategies do not work, but I'm saying that you can think about it and try to come up with situations where it doesn't look reasonable and verify that it doesn't work. Okay. And once it doesn't work for even one example, you can throw it away, saying that this is not good. Unfortunately, since we are doing greedy on Wednesday and we did dynamic programming on Tuesday, we could always go back to dynamic programming and give up on it. Okay? Nothing will go wrong. But our goal is to see whether greedy works, and I will, towards the end of this lecture, I mean not the second lecture, I will tell you why greedy is important. It's not, it rarely works in these kind of situations, but it's very important. Okay, so this leaves us with only one hope among at least the ones that we did, which was one that was suggested earlier, which is so one thing you can do is that three examples that we saw before are okay. So supposing I go to the first example, I pick the one that ends first. I'll pick the first black. That will knock off the blue, and then I'll do the second black. What was the second one? The first one that ends first is the leftmost red. That will rule out all the remaining reds. So those reds get eliminated. But now among the remaining, the one that ends first is the first black. So I will pick that. The blue goes out, and so on. Okay? So the latest, if I choose the earliest ending time and go in that order, these two examples work. And certainly it works here also because the black thing ends last. So if I pick the earliest ending time, I'll pick the first of the small red guys and then the second of the small red guys and so on. So I'll pick, anyway, once I pick the first red guy, the black is gone because they overlap. Okay? So at least these three examples or these three situations are compatible with the fourth strategy, which is to pick the earliest finishing time. So then, if that is true, then we have to justify why it is correct. Okay, so let us, before we prove it, let us just describe the algorithm. Okay, so we sort the request by their ending time, the last date on which they want. Okay, so we will have requests. So we have sorted it, so we will assume that end of R1 is less than or equal to end of R2 less than or equal to. But we are not guaranteed that the start of be before. Right? It's not guaranteeing that if I finish R1, then I can do R2. No. Because R1 ends before R2, but R2 started before R1 ends. In which case, if I do R1, then R2 is ruled out. Okay? I'm just saying that I've sorted it, so I can assume that whatever is given to me is sorted by ending time. Each one comes with a start time and an end time. Okay? It's given to me in some order. Maybe I close bookings for February by Jan 20th or something. So the orders might have come in any sequence. So somebody might have booked an early part of February in the end of the time. Somebody might have booked a late part in the early time. So the orders in which the requests came in a particular sequence, and they are kind of random with respect to the start and end time. Once I have closed the bookings, I now sort them. So now I have reordered them as R1 to Rn, such that each one ends before the next one. Now the algorithm just says start with R1. Okay. So you pick the first guy in your current list, because the first guy can always be scheduled because it is not conflicting with anybody. Once you pick the first guy, you knock off everything else whose starting time is before this ending time. They could be later on in the sequence. There could be something which ends very late which starts now, like that first example. Okay, the example with those short red jobs and one long black job. Right? So if I sort by ending time, the black thing will be the last. But it will conflict with the very first red guy, because the first red guy's ending time is after the starting time of the black. So you knock off everything which you can no longer accommodate as a result of choosing R1. Right? And having done that, now you have among the remaining things are what used to be called R2, R3 and all that, you have a new list of some of those jobs remain, some of those jobs are thrown out. So renumber them as R prime 1, R prime 2 and all that. So again you have a list I claim of jobs which are sorted by ending time. Because they were already sorted by ending time and some of them you have thrown away. Keep it in the same order. Now again the first one in that can be done because it did not overlap with my first R1. So I pick that. Again I prune R prime 2 to R prime whatever with those that are incompatible with R prime 1. Okay. Now at some point all the jobs will go away because nothing is left. I have chosen one which knocks off everything. And then I stop. So this is my strategy. Now the claim is this should be optimal in terms of the number of jobs. Now remember, like we said for that change example, if I had a 3 rupee coin, there may be two different ways of getting the same thing. So here also the choice may not be unique, right? So I might have supposing I have something like this. So what is my algorithm give me for this? What is the one it will choose first? It will choose the one with the, so it will order them as 1, 2, 3, 4. Okay, so this is R1, R2, R3, R4. Right? Because we are ordering it by the finishing time. So this finishes first, then this, then this, then this. Now I will pick R1, then I will say this goes. Okay? Because if I pick R1, I can't do R2 anymore. Now my new list is R3, R4. So then I will pick R3. Okay. Then this goes. And now I have the empty. I no longer have any requests pending, so I can stop. So I pick 2. But is this the only way to pick 2 here? No, right? I can pick R1, R4, I can pick R2, R4, I can pick R1, R3. So there are many different ways I can do this. Okay? So there are many other ways. Right? So that is what makes this proof a little bit tricky. Right? We are not saying that there is a unique solution and I am going to find it. The solution is unique in the sense that yes, whatever solution I pick will have only 2 requests in it. But which 2 requests, there may be different ways of having it. So somebody else might have a different strategy which produces 2 requests. I have chosen one strategy which produces 2 requests. Right? But when I'm proving that this thing works, it must just, you have to be able to show that it will always produce the minimum even though there are many ways of achieving that minimum. Right? That's the tricky thing. This happens to choose one particular way of achieving that, or maximum rather. Right? We are trying to achieve the maximum number of requests that we can accommodate. We are choosing one way to do it, but there are other solutions. Right? We choose to ignore those solutions in the examples that we have done, but another algorithm may have a different strategy. And what if that algorithm produces a different answer? Right? So that's what we have to prove. So we have to prove let's call it A. So supposing somebody else has used some different strategy, maybe they've used dynamic programming, I don't care. Okay? And they have come up with a strategy to pick the minimum number of, the maximum number of requests that can be simultaneously satisfied. I have my greedy strategy which produces what I claim is the maximum number of requests. I have to argue that my thing is at least as good as the dynamic programming guys. Okay? We are not talking about efficiency. We are only talking about the final answer being correct, because greedy, that's the thing, that you have to first justify that your thing always produces the correct answer. Then, as we said earlier, because you're typically examining fewer choices, it will usually be more efficient than the other strategy. Okay, dynamic programming will typically take more time because it is trying to exhaustively but cleverly look at all options. So if you can prove it is correct, usually the rest is guaranteed. You still have to justify what the complexity is, but the rest will work. So our algorithm picked some k things. Right? We can assume that these are in time order left to right. That R1 is the first of the request, R2 is second of the request. So these things do not overlap. Okay? But I'm presenting it in the order in which our algorithm will pick them, and our algorithm we know picks it left to right. Right? So we will pick some. So they will have some property like this. Right? So R1 will end before R2 starts. Okay? So this is, so out of the n requests that came, our algorithm produced a solution of size k. It says k of these requests can be satisfied. Okay? And these k requests are selected in this order. Okay? Now we have another hypothetical algorithm which is given to be optimal. and it picks because it is optimal, it picks a number which can be simultaneously satisfied and it is the maximum possible. We have claimed that we can do it with k. So what it picks must be something which is k, but it could be more. This is the problem. We have to justify that k is actually equal to m. That's what we need. Okay? But we can assume that this m things are also presented to us in the same way. In the sense that even though the algorithm might have picked it in some very different way. Okay, for example, we saw that if you pick minimum conflict first, you might first pull out a request from the middle, and then pull out something at the beginning, and then pull out something at the end, and so on. So the order in which it produced the answer may be very different, but finally, once it has produced the answer, I can order it from left to right, saying that these are the m jobs with the algorithm O produced, but the first of those jobs in time order is R1 prime, the second one is R2 prime, and so on. So this order is not the order in which, I'm not arguing that O actually produced it in this order. I'm saying that finally O presented me with m mutually compatible requests. These mutually compatible requests do not overlap. So I can take the first one and call it R1 prime, second one and call it R2 prime, and so on. Right? So these also have this kind of so both what we picked and what O picked can be ordered left to right in this. Okay? So now what I'm going to claim that step by step, I'm going to claim that R1 must end before R1 prime. And I'm going to claim that R2 must end before R2 prime. And here R3 must end before R3 prime. So inductively, I'm going to show that for each I up to k, for these k requests that I have picked, each of these Ri's ends before the corresponding Ri prime in the other person's list. Is it clear what I'm trying to prove? So I have got a solution which gives me k jobs. The optimum algorithm has produced a solution which has m jobs, which is at least k. It could have k plus 1, k plus 5, it could have more than k. I have ordered them both from start to finish order. And now I'm going to say one by one. If I pick my first job and your first job, my first job ends before your first job. So my request ends before your request. Then I'm going to claim my second one ends before your second one, and so on, all the way up to k. Is it true that R1 ends before R1 prime? So what is R1? R1 is the algorithm, is the request that our algorithm picked first. What is the property of R1? What was our strategy? Sort by end time. So R1 has the earliest end time of every job in the queue, of every request that is pending. Right? So it cannot be later than R1 prime because R1 prime at best can be R1 or an equivalent job which is the same thing. Right? Notice that we do not rule out situations that two requests could end on the same time and all that. So R1 prime could be a different request which also ends at the same time. But it cannot end any earlier. Because if it was earlier, then I would have chosen it. Okay, so R1 definitely ends no later than R1 prime. They could, I'm not claiming they're the same solution. Okay, I'm just saying that my solution at this point has occupied no more time on the time scale than your solution. Right? So now in general, come to a situation, I claim that now I have somehow shown so when I'm doing R2, for example, I have shown that R1 ends before R1 prime. Now, so if I look at the next, so supposing this is the picture. Now I want to argue that Ri ends before Ri prime. Supposing it doesn't. Okay. So is this possible? So what would I have done? What does algorithm A, our algorithm, do at this stage? It takes everything to the right in the original list, anything which ends later than this, and throws away everything which overlaps and keeps the rest. Okay. Now notice that this point is to the right of this point, or at least below. It is not to the left. Therefore, this point cannot overlap with this point because it doesn't overlap with this. So it cannot overlap with that. Right? So at the end of this, I claim both of these things are there. This because my algorithm has produced it, and this because by this argument inductively that this ends before this must be compatible. Okay? So now which would my algorithm choose? It chooses the one which ends first. Right? So if R prime I actually ended before Ri, I would have picked it. Okay? The claim at this point is that so if this R prime A actually ends strictly before Ri, I would have picked it. So if you claim that R prime A is not equal to Ri, and I didn't pick it, then it must be that they either end at the same time or Ri ends earlier. Okay. So is this clear? So this is the induction. Assuming that the I minus 1th job has the property that I said, the ith job must have it. Okay. So I can start with 1 by the base case. The first one has to be the earliest one. And then at each step, I can go from I minus 1 to I. Okay. And then finally what happens is that so up to k, I have shown that. I produced only k requests in my solution, and I have proved that up to k requests, my request ends no later than the algorithm O's kth request. And now suddenly, mysteriously, the algorithm O claims it produces some more requests which are compatible, whereas my algorithm stopped at Rk. Is that possible? So when does my algorithm stop? My algorithm stops when there are no requests to the right of the last request I chose. There are no more requests to the right of that in ending time, which are compatible. So therefore, if these things are compatible with R prime k, okay, so these must also be A could not have stopped. nothing there. That is only a false assumption that there is actually something to the right. Okay. So this basically shows that you need to prove, so the point of this exercise is that you need to prove something about the algorithm in situations like this against some arbitrary optimal algorithm. And the two solutions that you are comparing are not going to converge. Okay? So the so I produce a schedule which has k jobs, and this algorithm O produces a schedule which also has k jobs, but the two sets of jobs need not be the same. As we saw in that example, there may be many different ways of scheduling two comparable requests, two compatible requests. Okay, so I can't say that mine is the only solution. Okay, but what we show is that the solution right? So we basically prove some inductive property saying that I can prove that as I proceed down and compare my solution to that solution, my solution at every stage is at least as good as that solution. And therefore, if it's every stage at least as good, it can in the end produce something no worse. So though I have no idea what O does, as I said, O could be doing very complicated, it could even be doing exhaustive search. I mean, O could be just a thing which just tries out that research the tree of possibilities, right? Pick the first request, don't pick the first request. Pick the second request, don't pick the second request. It could be doing anything. Okay, so maybe somebody is actually calculating all those exponentially many choices and picking the best one. But still I claim it cannot do any better than this. Okay? So then of course there's always this, so we have proved correctness. This I claim is the hard thing. Okay. So what is the complexity of this? Yeah, so the complexity, there is a hidden step, right? So sorting, how long is sorting take? Now, after we sort, the way I had said it is that I pick the first one which is remaining and I throw away all the incompatible guys. Right? So, in principle, if I do R1, then I have to scan R2 to Rn to check if they are compatible, keep them. So, I have to scan n times. Then R2, I possibly have to scan n minus. Supposing they are all disjoint. Then R1 will allow R2 to Rn. R2 will allow R3 to Rn. So, I will have to do order n minus 1 comparisons, then order n minus 2 and all that. So I'll end up doing iteration. So I choose n jobs, and for each job, I end up scanning the rest. So I'll have summation 1 plus 2 plus 3 plus, or n minus 1 plus n minus 2, which will be n squared. Okay? But I claim I don't have to do that. Okay? So what I have to do is I look at R1, I keep it. I look at R2. Either I keep it or I drop it. If it starts before R1 ends, I drop it. I go to R3. I don't have to scan the whole thing and reduce the set and all that. I think it can only happen in this order. So I look at R1, I look at R2. If I don't like R2, throw it away. Go to R3. The first one that I don't throw away, I keep. Right? What I'm saying is that that conceptual step of pruning the list of jobs doesn't actually have to be done. I can just do it left to right and just keep every job that is not which is not contradicting my earlier choices. So I can do the remaining in a single scan. you see the thing, I choose R1. My earlier suggestion was you choose R1, then you look at R2 to Rn and see which ones are still useful. That requires an order n scan. So for R1 I do order n, for R2 I do order n minus 1. So n plus n minus 1 plus n minus 2 is basically summation 1 to n, which is n into n minus 1 by 2 or n into n plus 1 by 2, depending on how you count it. Okay, so it's basically order n squared. Okay, so we don't want to get into that. Because I claim that if you do dynamic programming, actually you'll do it in n squared. So this will be again. So basically, then it follows that because the sorting is actually the crucial step. Once you have sorted it, it's actually a linear time method. So we have 3 minutes. So what I'll do is I'll just pause the next column and come back. So is this clear? Is there any doubt about this? Okay, so I want to emphasize again, the hard part of the proof is the fact that the solution that you are producing is not unique. If there is only one answer, it's a lot easier to prove that your algorithm is correct. If there are multiple answers and they all satisfy a similar optimality criteria, then it's a little harder because you have to show that, no matter how you do it, you will produce the same end result. So that's the hard part. So let us now assume that we have, say, a photocopier. Okay, and then we have requests. So it is whatever, BTech project time, and you have the rock shop outside engineering college, and everybody's come to you to get their thesis photocopied, right? Everybody's thesis has to be photocopied. Some of them are smart and they give it to you early, saying I only need it 10 days from now. Some of them say I need it tomorrow. Okay? Some of them are 200 pages, some of them are 50 pages. Okay? And you have only one Xerox machine. So your obligation is to finish all of them. So you must and you do it one after another. So each one of supposing, so let's assume that your thing prints say 1 page a second. Then the 50 page thing will take 50 seconds. Then the 100 page thing will take 100 seconds and so on. But you are free to reorder. You're given all of them. You look at them. You know how much time each of them is going to take, and you know which ones are the ones which need to be delivered fast, right? So you fix the schedule. Okay. So in the process of fixing the schedule, supposing 2 people give you a very large thing which needs to be done by this afternoon, you may not be able to do both of them. Right? So one of them is going to overshoot deadline. So what you want to do is to it's a bit complicated. Minimize the maximum delay. So supposing I have all these things, so somebody's job was 7 hours late, somebody's job was 24 hours late, somebody's job was 13 hours late, and so on. So among all these delays, I pick the largest delay. Okay? And 24 hours happens to be, so in that example, so I count my inefficiency as 24 hours. It would have been better to give them all 10-hour delays, for example. Okay? This is not how Indian Railways work. When Indian Railways says that they have 95% on time, they are counting number of trains which are on time. So one train could be 3 days late, and it's only counted as one delay. Okay? But this is not how we would like. We don't mind if all flights at the airport are uniformly 15 minutes late. But if one flight is 5 hours late and the others are on time, then people will, that one 5-hour flight will be uniformly unhappy about it. Okay? But this is that kind of situation, right? So you want to not penalize anybody too much. So everybody is willing to accept a small delay, but nobody should have an undue delay. So you want to minimize the maximum delay. Right? So given all the requests and given the delay information about how much time each takes and how much time, what is the deadline that they have to achieve, we want to arrive at an order in which to do these requests to minimize the maximum delay. So this is it. We'll take a break and come back. You can think about it.